Hello students. In this fifth part on integration, we are going to study definite integration, which means integrating within limits. This is a very important topic. So in the first part on definite integrals, we are going to see the concept and some examples based on it. In the second part, we are going to study some special techniques for definite integration. So do subscribe to the channel. So what is definite integration? A definite integral is generally denoted by integral a to b fx dx, where a is called the lower limit and b is called the upper limit. So it is basically integration within limits. Now by definition, how do you define definite integral? Integral a to b fx dx is if the integral is capital Fx within the limits a to b, its value will be f of b minus f of a. Means in simple language, you first find the integral, then put the value of upper limit in it minus the value of the lower limit. So what are the properties? First property is the definite integral has a unique value. This is very obvious by the definition. It will have a unique value. Unlike simple integration. In simple integration, we just add the constancy which can take any value. But here, since we put the limits, the definite integral will have a unique value. The value of the definite integral in the interval a to b is the difference between the value of f at the end points. Basically, f is the antiderivative or the integral. The definite integral can also be found as a limit of a sum. This is a special case. Why? Because you know integration means it is summing up. So you can also have a definite integral as a limit of a sum. We will discuss examples based on this afterwards. A definite integral gives a single numerical value representing the net signed area under a curve of a function between two specified limits, which are known as the lower and upper limits of integration. So you can see in the diagram, if suppose a and b are the lower and upper limits, it is basically the area under the curve within these limits. And why signed area? Because you can also have on the upper side and lower side, means negative or positive. So it is the total area under the curve of a function within the specified limits. This is the definition. Also, for integral a to b fx dx, what is needed is f has to be well defined, and obviously it has to be continuous in the integral, in the limit a to b, in the interval a to b. The first fundamental theorem of integral calculus. Let small f be continuous on interval a to b, then capital Fx is integral a to some x ft dt. Then f is differentiable on AB and f dash of x is fx. See, this is nothing but you know that since integration is antiderivative, when you again take the derivative of it, you get the function itself. So, for example, if suppose capital Fx is integral of minus 5 to x, where x can be any value of the function t square plus sin t dt, then when you take the derivative of it, you get the original function, means f dash of x is x square plus sin x. This is our function. So when you take derivative of antiderivative, obviously you get the same function. So this is simply the first theorem of integral calculus. The second fundamental theorem of integral calculus, this is nothing but the definition of definite integral. If small f is continuous on interval a to b, then capital F is any antiderivative, means the integral of small f. Then integral a to b fx dx is fb minus fa. This is basically the definition of definite integral. The notation, you can sometimes also write it as capital Fx in the range a to b. A simple example to understand definite integration. Suppose if I want to integrate the function 0 to 4, the limits are lower limit 0, upper limit 4. The function is 4x minus x square dx. The first thing is you find the integral, then put the limits. So integral of 4x, that means 4 into x square by 2. That is nothing but 2x square. X square integral is x cube by 3. So now this is the integral. First put the upper limit, means put x is equal to 4. So you get 2 into 4 square minus 1 upon 3 into 4 cube. Minus, now put the value of x as, over here the lower limit is 0. So put 0, it can be anything. So it is 2 into 0 minus 1 by 3 into 0. So the whole value, a unique value will be there for definite integration. The value of this definite integral is 32 by 3. Now some basic properties with definite integral satisfies. The sum and difference of two functions, when you integrate them, you can write it as the first function plus or minus the second function. Integral of the first function plus or minus the integral of the second function. Same way, multiplication by a constant, you can take the constant outside. Reverse integral means if you have integral a to b fx dx, that is same as minus of integral b to a. Means when you reverse the limits, you have to put the negative sign. It will be negative of the original integral. Zero length integral means if you have the lower and upper limits same, then obviously area under the curve will be 0. So integral will have the value 0. Adding of integrals means adding of limits basically. If you have integral a to b and b to c, when you add both of them, the function is same. So you can directly write it as integral a to c fx dx. These are some other properties of definite integrals. They are very useful in solving the examples. I will explain each of them by taking an example later. We start with the first example. Integrate dx upon 4 plus 9x square within the limits 0 to 2 by 3. Now see, we can use all the rules of integration over here. Only thing is it will not have the constant c because you have the limits. So first thing is the denominator, you can write it as, take out 9 common from the denominator, you can write it as x square plus 4 by 9. So outside you will have 1 upon 9 into integral of 0 to 2 by 3 dx upon x square plus 4 by 9. So it is of the type dx upon x square plus a square. What is the integral? 1 upon a tan inverse x by a. As I told you, c will not be over here. Now what is your a? Your a is 2 by 3. So it is 1 upon 9 into 1 upon 2 by 3 tan inverse of 3x by 2. Now 1 upon 2 by 3 also take outside. So 1 upon 9 into 1 upon 2 upon 3. So it is basically 1 upon 9 into 3 by 2, which is 1 by 6. Into bracket you have tan inverse of 3x by 2. First put the value of x as 2 by 3. So it will be tan inverse of 1 minus put the value of x as 0. That is tan inverse of 0. You know tan inverse of 1 is pi by 4 and tan inverse of 0 is 0. So the answer to this is pi by 24. Next example. Integrate integral 0 to 1 x e raised to x plus sine of pi x by 4 dx. There are two terms. We will integrate each of them individually. So I can be written as I1 plus I2. So I1 means the first integral is 0 to 1 x e raised to x dx. What is the multiplication rule for integration we have studied? Integral u v dx is u into integral of v dx minus integral du by dx into integral v dx whole dx. So choose your function u as x and v as e raised to x. Just use this formula like we have done previously in integration. So what do you get is e raised to x integral is e raised to x. Derivative of x is 1. So you get the whole integral as x e raised to x minus e raised to x within the limits 0 to 1. So first put the value of x as 1. So it is 1 into e raised to 1 minus e raised to 1. So e minus e minus next thing is you put the value of x as 0. So first term is 0 minus e raised to 0 is 1. So the answer to this particular integral is 1. Second integral is integral 0 to 1 sine of pi x by 4 dx. What is the integral of sine? It is minus cos. Upon, you know when it is sine of kx type, so you have to divide by k. So upon you have to divide by pi by 4. It is cos of pi by 4 into x upon pi by 4 with a negative sign within the limits 0 to 1. So now when you take that constant pi by 1 upon pi by 4 minus 1 upon pi by 4 means minus 4 upon pi outside, integral is cos of pi x by 4 within the limits 0 to 1. So first put the value of x as 1. So it is cos of pi by 4 minus put the value of x as 0, that is cos 0. Cos pi by 4 is 1 upon root 2, cos 0 is 1. Put the limits, so you get minus 4 upon pi 1 upon root 2 minus 1. Add both of them. So our final answer will be I is equal to 1 plus 4 upon pi minus 2 root 2 upon pi. Correct? This is the answer to the definite integral. Next example. Prove that integral 1 to 2 1 upon x minus 1 upon 2x square into e raised to 2x dx is equal to e square into e square minus 2 upon 4. Now, in integration we have seen that there is a very important formula. Integral of e raised to x into fx plus f dash of x is simplified as e raised to x into fx. So now instead of e raised to x we have e raised to 2x. So here first we will use the substitution method. We will substitute 2x as some t. So let 2x is equal to t, differentiate both the sides. So 2 into dx is equal to dt. Why? Because dx we have to change to dt. So dx is dt by 2. Now let your function f of t be 1 upon t. T is 2x. So your function f of t is 1 upon t, which is basically 1 upon 2x. So what is f dash of t? T raised to minus 1, derivative is minus 1 upon t square. But what is t square? T square will become 4x square. So basically f dash of t is minus 1 upon t square, which is same as minus 1 upon 4x square. Before putting these values, we will have to change the limits of integration. Remember, whenever you use the substitution method, you are substituting some another variable. So the limits of the original variable will also change. When x is 1, what will your t be? 2x is t. So when x is 1, t is 2, and when x is 2, t is 4. So now instead of limit 1 to 2, your limit will become 2 to 4. Now just see, you have in the original function 1 upon x. So if I multiply and divide by 2, it is 2 into 1 upon 2x, means it is 2 into f of t. Plus you have 1 upon 2x square minus 1 upon 2x square. This is nothing but again you multiply and divide by 2. So it is 2 into f dash of t, because what is f dash of t? Minus 1 upon 4x square into e raised to t. Instead of dx, what will you write? Dt by 2. So take out 2 common and you are dividing by 2, so that will get cancelled out. So now your I is integral 2 to 4 ft plus f dash of t into e raised to t dt. Now you can directly use our formula. What is its integral? Its integral is e raised to t f of t within the limits 2 to 4 over here. So now first put the value of t as 4. So it is e raised to 4 minus upon 4 minus put the value of t as 2. So it is e square by 2. So it is e square by 4 into bracket e square minus 2. Correct? So now you have proved that the above integral is equal to e square by 4 upon e square by 4 into e square minus 2. This formula becomes very useful and you can solve the example very easily. So next example, you have to evaluate integral 0 to pi by 2 root of sine phi into cos raised to phi d phi. Now remember over here we are having root of sine phi. So we will use the method of substitution. Sine phi is equal to t. Then taking derivative it will give us cos phi d phi is dt. Now also you have one term which is cos raised to phi. So for cos phi you can write it as root of 1 minus sine square. So it is root of 1 minus t square. So what will be cos raised to 4? It will be 1 minus t square whole square. Always don't forget, when you are using substitution method, you have to change the limits. So when your phi was 0, your t will become sine of 0, which is 0. And when phi is pi by 2, t will become sine pi by 2, which is 1. So now the original integral. In the original integral, first thing is cos raised to phi can be write as cos raised to 4 into cos. Why? Because you know that d phi you have to change to dt. So you know that d phi is dt upon cos phi. So if I take one cos outside, then cos phi d phi is dt. Correct? So now our original integral will become integral 0 to 1 root of sine means root t into cos raised to 4 which is 1 minus t square whole square into cos phi d phi which is dt. Now this is very simple, just open the square, 1 minus t square whole square multiply by root t. So you know that integral of any t raised to n is t raised to n plus 1 upon n plus 1. Now put these values, first put the value of t as 1. So when you put the value of t as 1, it is 2 upon 3 minus 4 upon 7 plus 2 upon 11. Minus when you put the value of t as 0, all the three terms will become 0. So the final answer is 2 upon 3 minus 4 upon 7 plus 2 upon 11 which is 64 upon 231. Next example, evaluate integral 0 to 1 sine inverse of 2x upon 1 plus x square dx. Now remember, whenever you are having inverse function sine inverse, try to convert it in the form sine inverse of sine, because sine inverse of sine of theta will become theta. Second thing is, since it is 2x upon 1 plus x square, you can use a trigonometric formula sine theta is equal to 2 tan theta by 2 upon 1 plus tan square. Now over here, suppose if you put x as tan theta, then taking derivative on both the sides, dx is sec square theta d theta. So 2x upon 1 plus x square will be 2 tan theta upon 1 plus tan square theta, which is sine of 2 theta. Now whenever you are using substitution method, you have to change the limits. So when x is 0, your theta will become 0. And when x is 1, your theta will become pi by 4. Why? Because you know tan pi by 4 is 1. So now our original integral will become equal to integral of 0 to pi by 4 sine inverse of 2 theta into dx. What is dx? Sec square theta d theta. So now it is integral 0 to pi by 4. Sine inverse of sine is just the angle, which is 2 theta over here, into sec square theta. So now it is 2 into integral of 0 to pi by 4 theta into sec square theta d theta. So now we can use our multiplication rule for integration. It is theta into sec square theta. So take the first function u as theta and the second function v as sec square theta. Why? Because you know the integral of sec square. Now it is 2 into bracket, what is the formula? U into integral v dx means theta into integral of sec square theta minus integral of du by dx. Derivative of theta with respect to theta is 1 into integral of sec square theta. Now you know integral of sec square theta is tan theta, so put that. So now it is 2 into bracket theta into tan theta minus integral of tan theta is ln means log with the base e of mod of sec. So it is ln of mod of sec theta. Now this integral is within the limits 0 to pi by 4. So first put the value of theta as pi by 4. So 2 into pi by 4 into tan pi by 4 is 1 minus ln of what is over here sec pi by 4. Sec is 1 upon cos, correct? So it is 1 upon root 2 which is root 2. So it is ln of root 2 minus, now you put the value of theta as 0. So first term will come 0. Second term you know that sec 0 is again 1. That means it is ln of 1. ln of 1 is 0. So it is now simplified as 2 into pi by 4 minus ln of root 2 which is equal to pi by 2 minus ln of 2. Obviously note over here that 2 into ln of root 2, we have taken 2 which was outside the bracket. When we multiply by pi by 4 it is pi by 2, and 2 into ln of root 2 is log of 2 raised to half into 2 which is log of 2. Also ln over here means it is log with the base 2. So the final answer to this is pi by 2 minus ln of 2. Next example, you have to find the value of the integral 1 upon 3 to 1 x minus x cube whole raised to 1 upon 3 upon x raised to 4 dx. Now see, this is a little bit difficult example. In the sense you should know what you have to do. Now generally when you see this, the numerator, you will be taking out x outside. But you have the numerator raised to 1 upon 3. So what you have to do is you have to take out x cube. From the numerator take x cube outside. So it will be, first term will be x upon x cube, next term will be minus 1. So now what you have is x cube raised to 1 upon 3 into 1 upon x square. X upon x cube is 1 upon x square minus 1 raised to 1 upon 3 upon x raised to 4. So the first term will become x. So our integral will become integral x into x raised to minus 2 minus 1 whole raised to 1 upon 3 upon x raised to 4. Now one x will get cancelled, so you can write 1 upon x raised to 3 as x raised to minus 3. Now what we do over here is we multiply and divide by minus 2. Why we do this you will just come to know, because we want to use the method of substitution. So what we are doing over here is you take out minus 1 upon 2 outside. So you are multiplying and dividing by minus 2. So now multiply minus 2 with x raised to minus 3. So the second term will become minus 2 into x raised to minus 3. Now we will use the substitution method and you will substitute x raised to minus 2 minus 1, this term as t. So now we have substituted t as x raised to minus 2 minus 1. Taking the derivative on both the side, you get minus 2 x raised to minus 3 dx is equal to dt. Correct? Now always remember you are using method of substitution, so limits will change. When x is 1 upon 3, t is equal to x raised to minus 2 minus 1. So it is 1 upon 3 raised to minus 2 minus 1. When you simplify this will give you 8. When x is 1, it is t is equal to 1 raised to minus 2 minus 1, which is 0. So original limits have now changed to, lower limit has become 8 and the upper limit has become 0. So now our integral will become I is equal to minus half into bracket 8 to 0 t raised to 1 upon 3 into dt. Now you can understand why we multiplied and divide by minus 2, because minus 2x raised to minus 3 dx, this whole term has become dt. Correct? So now t raised to 1 upon 3 integral, you know it is t raised to 4 upon 3 upon 4 upon 3. So 1 upon 4 upon 3, which is 3 upon 4, take outside. So you have minus half into 3 upon 4 into bracket. Now here the upper limit is 0. So when you put t as 0, it is 0. Minus when you put t as 8, it is 8 raised to 4 upon 3. Just simplify this whole term. You will be getting the answer as 6. So the answer to this is 6. I told you previously that definite integrals can also be expressed as limits of sums. Just to illustrate this idea, suppose you are having a curve and you want to find the area under the curve. Now the area under the curve is the sum of infinitely large number of rectangles with infinitely small widths. You can see in the diagram that you can have infinitely large number of rectangles, each with infinitely small widths. Then when you add them all, these rectangles precisely give the area under the curve in the limit that their number tends to infinity. When you add all of them, you get that area under the curve. So basically integral a to b fx dx over here is limit n tends to infinity, summation of r running from 1 to n. H, what is your h? H is b minus a. The whole difference means the whole difference between the limits upon how many ever you are dividing your rectangles. So suppose if you are having n rectangles, so h is b minus a by n. So now what is this area? This area is h. What is the area of a rectangle? Width into the length. So over here h is the width and what will be the length? It will be f of a plus r into h. We will just take a small illustration to know what it means. So if we want to evaluate the series 1 upon n plus 1 upon n plus 1 up till 1 upon 3n as n tends to infinity. So over here it is n plus 1 plus 2 up till 3n, means it is n plus 2n. So I can write it as s is equal to sigma of r running from 0 to 2n 1 upon n plus r. Now over here, suppose if I take my x as r upon n, correct? Then this series I can write it as, from the denominator you take out n outside. So it is equal to 1 plus r upon n. So S will be equal to 1 upon n, sigma of r running from 0 to 2n, 1 upon 1 plus r by n. When you take your x as r by n, when your r is 0, x will also be 0. And when your r is 2n, x will be 2n upon n, which is 2. So now our original series can be written as S is equal to integral 0 to 2, 1 upon 1 plus x dx. Now you know this is integral is ln, means log with the base e, ln of 1 plus x within the limits 0 to 2. So first put the value of x as 2, then put the value of x as 0. So it is ln of 3 minus ln of 1, ln of 1 is 0. So your answer to this series is ln of 3. So this was the first part on definite integration. In the second part, we are going to do some more examples on definite integration using special techniques. So please do like and share the video and subscribe to the channel.